experiment, we got this another interesting illusion, auditory illusion, in an experiment by Deutsch, and this is the illusion of melodic channeling. And basically, let me show you here this picture. So basically, what we did was we played two different melodies into the separate ears. So in this ear, we played this melody, and in the left ear, we played this other melody. Now notice that the notes are broken up into low notes, high notes, and middle notes. And what was really interesting is the way the listener perceived the sounds. If we ask the listener to focus on what they're hearing in their right ear or their left ear, they heard either this or this. They heard this in their left ear and they heard this in their right ear. And what this tells us is that we're using this heuristic of separating sounds that are closely related in pitch, and segregating those sounds into separate groups. So most of the lower notes were perceived in the left ear because we started out low left, and most of the higher notes were perceived in the right ear because we started high right in this example. And it's really neat how even though these notes were being played directly into this ear and directly into this ear, we perceived it completely differently, only because of the way that our ears segregate, our brains segregate sounds according to pitch. Some of the other things that we use to separate sounds are proximity and time. Um, the sounds that occur in rapid succession usually come from the same source. So sounds that occur very close in time are generally come from the same source. We saw this when we saw it in the auditory streaming, when we were able to identify two separate streams. So not only did we separate the streams by pitch, but it was also by the fact that the streaming only happened when the sounds were very close together. So we were grouping those sounds together as if they came from the same source. The other phenomenon that we have in our auditory perception is this phenomenon of auditory continuity. That sounds that stay constant or change smoothly are usually from the same source. So if we hear a constant, like a siren or a baby crying or a jet engine, we assume that sound is continuously coming from the same source. Um, there was an experiment done by Warren, which is described in your textbook in, let's see, da, 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 da. I believe it is on page 307. Yeah, end of 306 and the start of 307. And it's a demonstration of auditory continuity. And basically, what he did was he played tones, and then the tones were separated. So you played like a constant tone, like a beep, and then but the tones were separated by gaps of either silence or white noise. If the tone was interrupted by silence, then the listeners perceived that the sound was stopped. So, which it was, of course, right? So I do a tone and then silence, tone, silence. The listeners are perceiving that the sound stops. But if I do that exact same experiment with the same tones, but I replace the same silence with noise, then what you're hearing is the sound continuing behind the noise. Let me see if okay. So here's an example, right? So here it is, right? So here are the tones: tone, silence, tone, silence. When we hear that, we perceive three separate tones. That there's a break. If I fill those gaps with noise, then it's really weird. What happens is even though the tone technically stops, we stop playing it and then it starts again, we still continue to hear that tone, even though it's not playing anymore. Um, we use top-down processing in processing sound. So the effects of our past experience, or what we understand, what we've learned from experience, is also affects our perception. Um, for example, if I were to play you the melody Three Blind Mice, but the notes are messed up so that I alternate between octaves. So instead of playing the higher octave version of the note, I will play the lower octave version of the note. You're going to find it very difficult to identify that it's Three Blind Mice. But if I first let you listen to Three Blind Mice, and then uh, do this test where I alter the octaves, you're going to do much better at identifying that song, because we have a new schema. We have a new experience in our schema that we can use to analyze that sound. So here's the example, right? This is the normal. So this is three blind mice, three blind mice. Um, so this is the song here with the octaves messed up, and this is the song here with the octaves normal. Um, we also have the ability to not only perceive, obviously, where things are located, and all of these different acoustic effects that we were talking about. We also have the ability to perceive meter, that is, to perceive the beat of a particular sound. And obviously, this is central to music. Whenever you listen to music, you can always, most people can pick up the beat right away and snap their fingers or clap their hands to the beat. If you've ever learned how to dance before, one of the things that you learn how is to step off and do the steps according to the beat of the music. The metrical structure is the underlying beat of music, and different types of music have different types of metrical structure. For example, this is the Star Spangled Banner, and the Star Spangled Banner has a metrical structure of 3 beats per measure. So the going from this line to this line is a measure, and each one of these quarter notes here represents one beat. So 1, 2, 3. This half note represents half a beat, and then these little notes here, these eighth notes, represent added together represent 1 beat. So each one of these measures has 3 beats in it, and it follows a very rhythmic pattern. Oh, say, can you see by the dawn's early light? Right? You have this pattern, this rhythmic pattern that flows in this particular music. Now, this figure is from page 310 in your book, and it's a really interesting study on the effects of language on perceptions of sound. As you know, different languages are made up of different rhythms and tempos, and it turns out that the language that you know, your primary language, your first language, affects the way you perceive things as simple as sound bursts. So in this experiment, English listeners and Japanese listeners were subjected to these bursts of sound, so short bursts and long bursts. So this is a short burst, and this is a long burst. Short, long, short, long, followed by, the repeating pattern. And what's really interesting is that and these were the exact same tones, the exact same sound bursts played for either English speakers or Japanese speakers. And the really interesting thing is that when we asked each one of the subjects in this study to say, did you hear short long or long short? They varied according to their language. So English speakers said that they heard short long, so papa, and Japanese speakers said that they heard long short, ba bop, ba bop, or ba bop, ba bop, like that. And it matches up with the patterns of the languages. English has a lot of like F and T plosives followed by a vowel sound. So two, four. So we tend to perceive these bursts as short long. Now, Japanese does not have those same types of sounds. Japanese is made up of a lot of more longer type sounds that are all strung together. So they perceived more the long short burst, which is really interesting. Again, this is top down processing. Based on your experience, you're going to perceive these sound bursts differently. There is a relationship between hearing and vision. We don't just use the sounds that are echoing through our ears to process sound. We also take in the visual stimuli that are around us to try to understand what it is that we're hearing. This is we see this with ventriloquism, right? If you've got a ventriloquist who is playing with a dummy, we very easily perceive the voice of the dummy as coming from that dummy, even though we know that the ventriloquist is producing the voice. It really does look like that voice is coming from that dummy. Um, in this experiment, there was an experiment done by Secular where, and it's shown on, let me see if I have the picture here. Yeah, here it is right here. Um, Basically, it was the exact same stimulus shown to subjects. So it looked like there were two balls rolling towards each other, and then and then they roll off in these directions. So they're going straight. So this one, oops, sorry about that. This one is going from here to here, and this one is going from here to here. If I show a subject this sequence, a little film with this sequence, but it's just silent, it looks like the balls are just crossing. But if I show subjects the very same film, but I add a clicking sound right here, we perceive the objects as colliding with each other. We perceive them as colliding, and it looks like they're colliding and then bouncing off of each other. This visual perception, again, is changed by the sound. So there is this really interesting interaction between what we perceive, what we hear, and what we perceive, what we see. Um, the interaction between vision and hearing is very complex, involving a lot of different, a very sophisticated, complex mixture of sensations. Thaler in 2011 did a study where he used expert blind echolocators to create clicking sounds. So these were people who were blind, and what they would do is they would click. They would make a clicking sound with their mouth. And as they made the clicking sound with their mouth, they would listen to the reflection coming back. And they would use that clicking sound to navigate through the environment. And what he wanted to see was how these clicking sounds and the navigation that underlied these sounds activated the brain. So, and he studied this and he found this mix, this very interesting mix of motor activation in our sensory motor cortex here, obviously auditory activation, and visual activation. So as we were listening, as these blind people were listening to these sounds, they were constructing using the visual part of their brain. Even though they're blind, they were using the visual part of their brain to construct some sort of representation of this world that they were navigating through. Um, we have here um, the fields that were studied in the cortex in this particular area when the subject was, say, focused on this particular spot in their auditory space. It also lit up a corresponding spot in their visual receptive field as well. Again, remember, these were blind people. Blind people, but the auditory feedback, the auditory information was being used to help these people build a model of the world that they could navigate through. And this model of the world was being represented in the visual cortex. And you can see there's a really nice overlap between the auditory cortex operating and the visual cortex operating. This image here is from page 313 in your book, and it represents again a blind subject listening to sound stimuli. And what's really interesting here, again, this is a blind human. Notice the activation in the back of the brain here. Now, this is the front of the brain, the back of the brain, top, and the bottom, and this is the side of the brain here. Remember, the back of the brain is associated with visual stimuli. And the stimuli that were listened to here in this picture was sounds with echoes. Okay, sounds with echoes. Now, what is it about an echo that's important? Echoes tell you the space that you're in. If you listen to echoes carefully, you can very easily tell, for example, what size of room that you're in and where things are. With some practice, the blind person, the same blind person here, was listening to sounds without echoes. So what's really interesting is that the person was using the echo information to construct in their visual cortex, to construct a representation of the world that they could then use in navigating and understanding their place in space.